Hi guys, welcome to another chemical engineering tutorial brought by the ChemEng student. In this lesson we're going to take a look at the plotting of a numerical integration using a Microsoft Excel calculator. So before we look at the development of the calculator, we first just want to take a quick revision of what numerical integration actually is. And numerical integration is simply a useful method for mathematical analysis when we have complex integration calculations. And we have two types. We have the trapezoidal rule and we also have the Simpsons rule. Now I'll put a link in the description to a previous video in which we look at the manual solving of numerical integration, but here we're going to see how we can implement this in Microsoft Excel. Now let's just take a quick overview of the two rules before we jump in to the Excel sheet. So the trapezoidal rule is essentially a way in which we split the area under the curve into equal sized rectangles. And we do this so that we try and match the slope of the curve. And each strip, we will find essentially the area of each strip and then combine the values to deduce the area of the curve. The more strips that we have, the more accurate our system will be. The formula for the trapezoidal rule is we have our delta x, so that is the thickness of our strips, divided by 2. We then have the first and final values within our data set added together, plus and then 2 times the summation of all the other values within that given data range. Now don't worry if this looks a bit confusing, we will look at it in a real life example in just a second. Now for Simpsons rule uses a quadratic curve in order to approximate the function within each of the given strips. So rather than it be complete rectangles, the Simpsons rule aims to map out the quadratic equivalent of any given shape. And the equation for Simpsons rule is, it comes in various different ways, but here we're going to summarize it in two key ways. This is the more formal, whereby we have our delta x over 3 multiplied by, now it's going to be the first and last values in the data set, then it's going to be plus, now it's 4 times the odd values, so the odd terms within the strips or within the range, we will group them together and multiply them by 4, and then we add 2 times the summation of all the even terms. Now you can do this one by one. So you could have 4 times y1 plus 2 times y2 plus 4 times y3 and so forth. But a more informal way that we can represent this is that we have the sum of the end terms, so that's the first and the last, 4 times the sum of the odds plus 2 times the sum of the evens. Now Simpsons rule is only applicable when we have an even number of terms, whereas the trapezoidal rule can also handle odd terms as well. Now for delta x, that is so we can see here, if we come back, delta x is the thickness of the strip. Now in order to calculate this, then we need to ensure that for our entire data set that delta x is equal. So it has to be the same size. If it's not the same size, then you will have to do several variations and several different iterations of numerical integration in order to capture the total area that we want. Now to determine the delta x, we use a simple formula of whatever our top limit is minus our bottom limit divided by the number of strips. So that's divided by the number of terms that we want to use. Now, before we jump into the Excel calculator, we just want to finally look at graphical representation of this. And that we can see in the trapezoidal rule, we have these various strips and rectangles that aim to try and map out the shape of the curve. Now, sometimes these aren't cut like this, they are just completely straight, and that is perfectly acceptable as well. But you can see with the Simpsons rule, it tries to use this sort of parabolic shape in order to map out. But you can see in both instances that there will be a degree of error because we have overshoots, which is the parts that go beyond the curve, and we have undershoots, which is the ones where they don't actually meet the threshold of the curve. And so both of them will have a degree of error, and depending on the characteristic of the curve, one will be more accurate than the other. So it really depends on how our graph looks. Now let's take a look at our Excel calculator. So our Excel calculator looks something like this. Now you'll be able to download this when the link in the description, but you'll also get access to lots of other types of calculators that are bespoke to both general mathematics and also engineering, and lots of other applications through our website, and more specifically our Microsoft Excel course, as well as many others. I'll put a link in the description to that, and it's a full CPD accredited course, which you can learn and get a CPD recognised certificate in Microsoft Excel as well. I'll put a link in the description to that if that's something that you would be interested in building and creating more elaborate calculators for different applications. But here, what we basically got is we have our data set, which is a time versus a velocity. So this is like perhaps a projectile that we fire into the air, and this is how it travels, and it reaches this maximum point and then begins to fall. So we've got this very parabolic shape. Now, just as a reminder that these are the formulas for the trapezoidal rule, and this is the formula for Simpsons rule. So you can see that we wrote it in its very raw form, where it was 4x1, 2x2, 4x3, and so forth. But we can put it into the software however we want. Now, we can take our data set here and we can perform a range of calculations. If we specify our upper and lower limits, then we can deduce what the overall value of the system is going to be. So for example, if we wanted to find the area under the curve in its entirety, then our upper limit would be here and our lower limit would be here. However, if we wanted only a specific point, so say for example, if I draw a line here, so if we take a line and say we want it from 10 seconds, and then we wanted another line, instead of between 10 seconds, we wanted it to 20 seconds. Then what we would essentially do here is we would be calculating the area enclosed in this space only. And so let's work out what that is in both the trapezoidal rule and in the Simpsons rule. So we first want to specify our upper limit. So our upper limit in this case is going to be 20. So I'm just going to highlight these, I'll put them in green, and our lower limit is going to be at 10. So that's the range of data that we're going to be working with. And so our upper limit here is 20, and our lower limit here is 10. Now our delta x is the difference between these two values. So each one is going to have a thickness of 2. So what we'll say here is that the difference between these, that each strip is going to be a length of 2. And then from here, what we can now say is that our f of x, which is going to be equal to, now open a bracket, and you have to be very, very careful with the brackets, because if the brackets are in the wrong position or you forget a certain bracket, then you're going to get the wrong value. So you just need to be very, very careful. So we take our delta x and we divide that by 2, like so. Now we're going to close that bracket and we're going to click times. We're going to open a bracket, and then we're going to say what is our initial value, which is 87, because that is the first point. Then I'm going to put plus, I'm going to open a bracket, and I'm going to put 2 multiplied, and I'm going to open another bracket. And I'm going to then take each one of these points and add them together. I'm not going to include the last one. And then if I close that bracket and close the other one, That's now encompassed this section here. And then finally I can put plus, and then my 120, close the bracket, and you can make sure that all the colours are lined up so we can see that black is now finished on black. So if I hit enter, we can see here we get 1075. So that tells us that the area under this curve is 1075 units squared. Now, if we do the same thing, but this time with the Simpsons rule, then our upper limit and our lower limit are going to stay the same. Our delta x is still going to remain as 2, but this time, if we equals, now we'll do the same thing. We have our delta x divided by 3 this time. Close the bracket. We'll then put multiply. Open this bracket. Now it's going to become the initial term, which is our 87, plus, now I'm going to just do the calculation of 4 times, and then I'm going to add all the odd terms. So this is the first odd term, this is the second odd term, and we don't have another. So that's the first and the third. Then we close those 2 brackets, then we put plus, open the bracket, and this time it's going to be 2 times, open another bracket, and it's going to be the C11 plus the C13. And that then encompasses the even brackets. So then if we close that, and then we need to add the final term, which is the xn, and then close the bracket, and we hit equals. Now, you can see here that there is a stark difference between the values, because the trapezoidal rule tells us that it's 1075, but with the Simpsons rule it tells us it's 998, so there is a high degree of error. But in this case, if we come back to what the difference in the trapezoidal and the Simpsons rule is, and how it maps your curve, then the Simpsons rule maps the curve as a parabola, or a quadratic. Now you can see our data set is a quadratic, and so the Simpsons rule in this case is going to be the most accurate. And so we would say that the area under the curve for this particular section is 998 rather than 1075. I might be saying, well, how can we visualize that? So if we come to the trapezoidal rule, which is like so, then what we can say here is that if we were to put in the number of strips for the entire system, then we can see that for each thickness of 2, that in order to encompass the area under the curve, we have a lot of overshoot on the trapezoidal rule. So if we were to add up all of these sections, that's what would give us the difference between the 1075 and the 998. So that overshoot is caused by all of these extra elements that area is being overshot compared to the data set or the parabola that we've created. And so that just helps you visualize what is actually going on in this particular system. And so in order for us to make an informed choice, we would say that under these conditions, the Simpsons rule is the most accurate because it maps out the more closer to the parabola or the quadratic that our data set encompasses. If we had a more linear set of systems, then the trapezoidal rule would become the more accurate. So it just depends. Now, of course, what we can also say is that if we reduce the size of delta x, then what that will tell us, or what that would do, is make it more accurate. So rather than have a delta x of 2, let's say we wanted a delta x of 1, then we can see that the values become significantly different. And so what that then will do is it is highly dependent on the thickness of our system. And again, we can determine what those values actually are. We can dictate what size or thickness we want our system to be. And we can do that again with our upper and our lower limit. That will tell us the number of strips, and therefore we can deduce the value of delta x. Alternatively, we can choose the delta x, and in this case, because each of these values differs by 2, the interval is the same, and so delta x is 2. So I hope that helps in understanding the concept and the idea of numerical integration using Microsoft Excel. As I says, you'll be able to download a copy of this as well as access more resources through our website. I'll put a link in the description to that, and you can check that out if you are interested in obtaining a CPD certificate in Microsoft Excel, which you can use for job interviews, you can use as your CPD development, and so forth. So thank you for your time, and don't forget to subscribe and like the channel. It really helps us reach as many students as possible. Thank you for your time, and we look forward to seeing you in another video.